Alright, in this video we're going to take a look at a relatively simple stoichiometry problem for a reaction that is in solution. So whenever my students look at this balanced chemical equation, some of them get scared because they see these AQs here and then these solids kind of hanging off the end there. The AQ just means aqueous, so that means it's in a liquid solution state, and the S just represents it's a solid. So don't let those phases of matter scare you. And the first thing we're going to do before we even read our problem is double check to make sure that my chemical reaction is balanced. In this case it already is. So I can go ahead and read my problem. It says, what volume of 4.0 molar potassium iodide solution is required to yield 89 grams of lead iodide? So I've actually already done this for you. What I like to do is kind of take these three things that are mentioned in the problem and then just plug them in kind of underneath my chemical equation here. So I'm really just given 3 bits of information. I'm asked to find liters, which is why I put a question mark by the liter. I know the molarity of this solution, it's 4, and then this is what I want to yield as my final product here. So using my molarity equation, right, if I write out my molarity equation, molarity equals moles per liter. If I look at the information that's given about this solution, well, I know I'm going to be looking for volume, that's going to be my X. I know I have the molarity, that's going to be 4, I can plug that in real quick. Really, the only thing I'm missing out of this equation is moles. So I'm going to try and solve for moles first. Whatever value I get for moles of this potassium iodide solution, I can plug it in right here. So let's go ahead and erase all that. And really, the only other bit of information I'm given is this 89 grams of lead iodide. So if I need to get moles of potassium iodide, I can go from grams to moles and use my mole ratios to end up with moles of Ki. So that's what I'm going to do here. Let me just erase this so I have space to write. Alright, so I'm going to start with 89 grams of lead iodide. And first thing I'm going to do is convert to moles, right? Because grams are not useful for me. I need moles. Everything's got to be in moles. So I'm going to put 1 mole up top, and then the molar mass of lead iodide down below should be 461. Where did I get 461 from? This is the molar mass off the periodic table. Okay, so if I were to stop my calculation right here, I would end up with moles of lead iodide. That's not what I need. I'm looking for moles of potassium iodide. So I got to go one more step, use my mole ratios here to get moles of potassium iodide. If I have moles of lead iodide up here, that means I have to have moles of lead iodide down below to cancel out. Mole PbI2, there we go. And then we can put moles of our desired unit up top here. So we can put moles Ki. Perfect. Now I can stop calculating. So again, what did I just do here? I went from grams to moles to my mole ratios to get moles of Ki, because this really is what I'm after. I want to be able to plug in moles of Ki into my molarity equation. Okay, so where do I go to find my mole ratios? That's another one of my favorite questions. You must look at your balanced chemical equation to find those coefficients. In this case, it's a 2-to-1 ratio, so I'm going to put the 2 up top, which will match with the Ki, and the 1 down below. So how do you solve this? If it's up top, we're going to multiply by it. If it's down below, we're going to divide by it. So punch in your calculator 89 divided by 461 times 1 divided by 1 times 2. So that's how you can solve this. If it's up top, you multiply. If it's down below, you divide. And for your final answer, you should end up with somewhere around 3.9 moles of Ki. Wonderful. Am I done? Can I just box this in as my final answer? Did I answer what the question was asking me for? Well, no. I just had to do all of this work just so I could get moles of Ki. So I am not done yet. Now I can take moles of potassium iodide and plug it back into my molarity equation and solve for volume. Because remember, the volume is really what we're after here. That's what the problem's asking me to find, is the volume of this solution. So once I plug in my molarity, the molarity is given to me in the problem. It will be a 4 molar solution. We just calculated moles. Now I have a value for moles that I can plug in here, 0.39 moles of Ki. Now I can solve for liters. And some of my students are really great with algebra and they can rearrange this equation in their head, and others look at that equation and say, gosh, I don't know how to solve for the unknown there. And this is where this triangle comes in handy. So I'm going to show this to you one more time. If you write the molarity equation in this funny little triangle, and you cover over the unknown variable, in this case the unknown variable is liters, so if I cover that over, almost like magic, the correct way to solve this equation kind of just appears. So you need to punch in your calculator moles divided by molarity. So in this case, punch in your calculator 0.39 divided by 4, and that should get you a final answer of, and I'm running out of space here, let me erase that, about 0.0975 liters, something along those lines, depending on how you round. That should be your final answer, and yes, we did answer the question. It was asking for volume of this Ki solution. This has been a Rodriguez original production. I hope you enjoyed. Go back, look at other examples, study your notes, practice, practice, practice. Good luck.